Welcome back. Let's learn how to find area using the cross product. Alright, so previously you were introduced to the cross product, which is another way of multiplying two vectors together. And in this video, we're going to look at one of the uses of the cross product, which is the ability to find the area of parallelograms and triangles with vectors. Alright, in particular, we're going to be using this definition of the cross product. I like to call it the alternate form of the cross product. I showed you where this formula comes from in my lesson on the cross product, and the formula goes like this. For two three-dimensional vectors, vector v and vector u, vector v cross vector u, or the cross product of those two vectors, will be equal to the magnitude of vector v times the magnitude of vector u times sine theta, where theta is the angle between those two vectors, and then you're multiplying all of that by a unit vector that describes the direction of that cross product. Alright, so this was another way to find the cross product between two vectors, given that you know their magnitudes, the angle between them, and the direction of that cross product vector. Okay, but now we're not necessarily interested in a vector in this case. What we're going to be doing in this video is calculating area, which is just a scalar value. So all we're going to be interested in here is looking at the magnitude of this cross product vector, okay? And all that's going to be is this definition, but without the unit vector, the direction, right? We can represent any vector by taking its magnitude and multiplying it by its direction. And that direction will be represented by a unit vector. So since the cross product of vector v and vector u is going to result in this vector, where this unit vector describes the direction, then what's being multiplied by that direction must be the magnitude. And so we know this, the magnitude of the cross product between vector v and vector u is equal to the magnitude of vector v times the magnitude of vector u times sine of theta, which is the angle between vector v and vector u. Okay, and so keeping this in mind, let's now take a look at a parallelogram and discuss how we would calculate its area using vectors. And so here's our parallelogram. Remember that parallelograms are four-sided shapes, or quadrilaterals, where the opposing sides are parallel. Okay, and so two of the adjacent sides of this parallelogram are represented by vector v and vector u. And it's important to notice here that both of these vectors start at the same initial point, right? They are directed away from this point. Vector v is pointing in this direction, and vector u is pointing in this direction. And then we have some angle between those two vectors. And so for this parallelogram, how would we calculate its area? Well, in general, the area of a parallelogram, I'm going to represent that with capital A sub p, p for parallelogram, that is equal to the base of the parallelogram times its height. Okay, and so the base of this parallelogram would be represented by this side, or the length of vector u, which we can immediately recognize to be the magnitude of vector u, right? The length of this side of the parallelogram, the base of that shape, will just be the magnitude or the length of this vector representing that side. So we could say that the area is equal to the base, which is the magnitude of vector u, times the height of that parallelogram. And so what is the height in this case? And be careful, it's not going to be the magnitude of vector v. This side doesn't represent the height. The height would actually be this measurement right here, all right? The measurement from the top of the parallelogram to the base of the parallelogram. And that height would be perpendicular to the base. It creates a 90-degree angle. It's a right angle. And so keeping that in mind, how would we determine what this height of the parallelogram would be equal to? Well, in order to find that height, which I'll represent with h, what we can do is make use of the fact that we have a triangle here, a right triangle, formed by vector v, the height, and part of vector u, and use what we know about our trig functions that relate the sides of a right triangle to an angle, and that should help us find that height. And so here's what I mean by that. Remember, so TOA. This tells us how we can relate sine, cosine, and tangent of an angle to the sides of a right triangle. Sine of an angle is equal to the opposite side divided by the hypotenuse. Cosine of an angle is equal to the adjacent side divided by the hypotenuse. And tangent of the angle is equal to the opposite side divided by the adjacent side. Now in this case, if we want to find the height, h, we want to work with at least the opposite side of the triangle from the angle, right? If this is our angle, the opposite side would be the height. So we know we're going to be working with either sine or tangent because they work with the opposite side. But then do we want to work with the hypotenuse of this triangle or the adjacent side? Well, the adjacent side would be this side right here, and we don't really know what that is. It's a fractional amount of the magnitude of vector u, so we probably don't want to work with that. Instead, we would want to work with the hypotenuse, the longest side of the triangle, because that would just be the length of vector v, or the magnitude of vector v. Okay, so let's use sine, because sine of theta will be equal to the opposite side divided by the hypotenuse, the two sides we want to work with. And so that will look like this. We'll have sine of theta is equal to the opposite side, the height, so we'll have h divided by the hypotenuse, which would be the magnitude of vector v. All right, so I'll write the magnitude of vector v, and now if we want to solve for the height, we just have to multiply both sides by the magnitude of vector v, and that will give us that h, the height, is equal to the magnitude of vector v times sine of theta, the angle between vector v and vector u. And so that's our height. That is the height of this parallelogram. So we can plug that into our area formula here. The area of a parallelogram is equal to the base times the height. We had the base, but now we also have the height. So let's plug that in. We'll have the magnitude of vector u times the magnitude of vector v times sine of theta, the angle between vector v and vector u, right here. And so now take a look at the result that we have. We can calculate the area of a parallelogram where two adjacent sides are represented by vector v and vector u by taking the magnitudes of those vectors, multiplying them together, and then multiplying by sine of the angle between those two vectors. And if you compare that to what we talked about earlier, the magnitude of the cross product between vector v and vector u, take a look at what that's equal to. We have the magnitudes of those vectors multiplied by sine theta, which is exactly what we have here. It doesn't matter the order in which we multiply them. We can swap the order of these magnitudes, and we have the exact same calculation. The magnitude of vector v times the magnitude of vector u times sine of theta. And so while we can certainly find the area of a parallelogram using this formula, that's totally valid, we can also find the area of a parallelogram by taking the magnitude of the cross product between vector v and vector u. It will be the same exact thing. So if we just know the components of vector v and vector u, right, if we know what those two vectors are equal to, but we don't know the angle between them, we can just take the cross product of those two vectors and then find the magnitude of that vector. That will also give you the area of a parallelogram where those vectors would be two adjacent sides. Okay, and so these two formulas right here, you can use to calculate the area of a parallelogram using vectors. But now if we take this one step further, we can also adjust these formulas such that we are calculating the area of a triangle where vector v and vector u form two adjacent sides. And here's what I mean by that. If we draw a line that connects the terminal points of vector v and vector u, these 2 points right here, that line would look something like this. You can see that with that line, along with vector v and vector u, we form a triangle. In particular, we form a triangle that would represent half of this parallelogram, right? We essentially divided this parallelogram into two equal halves, but one of those halves would be a triangle where two of the sides are vector v and vector u. And so since that triangle is half of the parallelogram, that would mean that the area of the triangle is half of the area of the parallelogram. Okay, and so if we wanted to calculate the area of a triangle where two of the sides are vector v and vector u, all we'd have to do is take half of the area of the parallelogram where two adjacent sides are vector v and vector u. So to calculate the area of this triangle, we would just need to multiply each of these formulas by 1/2. We would just take the area of our parallelogram and divide it by 2. Okay, and so that looks like this. The area of a triangle, where vector v and vector u represent two of the sides, that would be equal to 1/2 times the magnitude of vector u times the magnitude of vector v times sine of theta, or that area of the triangle would be equal to 1/2 times the magnitude of the cross product between vector v and vector u. All right, both of these formulas would allow you to calculate the area of a triangle where vector v and vector u are two adjacent sides that both start at the same initial point. Okay, we just took these two formulas for the area of the entire parallelogram and multiplied them by 1/2 to take half of that area, which will be the area of a triangle. Okay, so to summarize, if you want to calculate the area of parallelograms and triangles using the cross product, we have two different formulas in each case, and for both of those shapes, it's important that two adjacent sides are vector v and vector u, where they both start at the same point. For the area of a parallelogram, we can either find the cross product of vector v and vector u, and then find the magnitude of that vector, or we can take the magnitude of vector v times the magnitude of vector u times sine of theta, where theta is the angle between those two vectors. And then for the area of a triangle, we just take 1/2 of each of those formulas. All right, so the area of a triangle would be equal to 1/2 of the magnitude of the cross product of vector v and vector u, or 1/2 of their magnitudes multiplied together, multiplied by sine of theta, where once again, theta is the angle between vector v and vector u. Okay, and so those are the formulas you need to know for calculating area using the cross product. And so now that you have seen these formulas and where they come from and why they work, let's take a look at a couple examples. Okay, so here's our first example. We want to find the area of a parallelogram where two adjacent sides are vector v and vector u, and the angle between vector v and vector u is pi divided by 3 radians. Okay, so in this problem, we're actually going to use both of the formulas that we looked at for calculating the area of a parallelogram using the cross product. Typically, you really only want to do one of these. In most cases, you're going to end up using this first formula, where you're just finding the magnitude of the cross product between the two vectors. It's not very common that you're also going to be given the angle between those two vectors or those two adjacent sides. In most cases, you're just going to be given the vectors. But in this case, I wanted to show you that these two formulas will give you the same answer if you are given all of the information that you would need in order to use both of those formulas. Okay, and so let's start by using this version of the formula, where we take the magnitude of vector v times the magnitude of vector u times sine of the angle between those two vectors. That's going to be our first way of finding this area. And so in order to find the area of this parallelogram, we are going to need to calculate the magnitude of each of our given vectors. And so let's do that. The magnitude of vector v will be equal to the square root of the sum of its components squared. So we'll have 3 squared plus 3 square roots of 3 squared plus 0 squared. Now 3 squared is 9, and 3 square roots of 3 squared will be 3 squared times the square root of 3 squared. So that will be 9 times 3, right? The square root of 3 squared will just be 3. So we have 9 times 3, which is 27, and then 0 squared is 0. So this is equal to the square root of 9 plus 27. And 9 plus 27 is 36. So this would become the square root of 36, which is equal to 6. Okay? So the magnitude of vector v is 6. And then let's take the magnitude of vector u. That will be equal to the square root of the sum of its components squared, which is pretty easy in this case. Our components are 5, 0, and 0. So we're going to have 5 squared plus 0 squared plus 0 squared. 5 squared is 25, and then obviously 0 squared is 0. So we have 25 plus 0, which is 25. So this is just the square root of 25, which is 5. All right, so now we have everything we need to calculate the area of this parallelogram. Using this formula, we have the magnitude of vector v, the magnitude of vector u, and the angle between those two vectors. We're told that it's pi divided by 3 radians. So if you want to write that down, I'll write it right here. Theta is equal to pi divided by 3 radians. And so using these three values, let's calculate the area of our parallelogram. We'll have the magnitude of vector v, which is 6, times the magnitude of vector u, which is 5, and then we're multiplying by sine of theta, which in this case is pi divided by 3. Okay, we're just using this formula right here. The magnitude of vector v was 6, the magnitude of vector u was 5, and then we have sine of theta, which will be sine of pi divided by 3. Now, if we simplify, this will be equal to 30, right? 6 times 5 is 30, and then that's going to be multiplied by sine of pi divided by 3, which is the square root of 3 divided by 2. So we're multiplying by the square root of 3 divided by 2. And 30 divided by 2 is 15, so this is equal to 15 square roots of 3. Okay, so 15 square roots of 3 is the area of the parallelogram that has two adjacent sides, vector v and vector u, where the angle between them is pi divided by 3 radians. We found the area using this formula right here, but we could also find the area using this formula right here. We could simply just take the cross product of vector v and vector u, and then take the magnitude of that cross product. All right, because the cross product of two vectors is going to give you another vector, so then we want to find the magnitude of that vector, and that will be the area. And before we do that, I just want to make a couple notes about this answer right here. Since we are finding area, sometimes there may be units associated with that answer, and so whatever those units might be, could be centimeters, feet, inches, meters, whatever. Just remember that those units would be square units, okay? We are working with area, so 15 square roots of 3 would be a value of square units, okay? And then the other thing I wanted to make a note of is that if you plug this into your calculator for an approximate value, it's approximately equal to 25.98 and some more decimals, okay? So if you have a calculator that doesn't give you exact answers, this is what the correct answer would be if you get the approximate value and round it off a little bit. Okay, but now let's find the area of this parallelogram using the other method, the one that you will probably use most often, by taking the magnitude of the cross product of two vectors. Let's set up this cross product. We're going to be taking the cross product of vector v and vector u, and so remember, the easiest way to do a cross product is to set up a 3x3 matrix and then take the determinant of that matrix. And so that will look like this. Remember that the first row will always be the standard unit vectors. So we have vector I, vector j, and vector k. Then the second row will be the components of vector v, the first vector in our cross product. And then the third row will be the components of vector u, the second vector in the cross product. So our second row will be these components of vector v. So we'll have 3, and then 3 square roots of 3, and 0. And then this row will be these components, which are 5, 0, and 0. Okay? Now to calculate the cross product, what we want to do is look at our first row. In particular, we're going to start with vector I, and we want to cross out the row and the column that vector I is located in, and then use the remaining 4 values to calculate a 2x2 determinant. All right, we're going to be multiplying 3 square roots of 3 by 0, and then subtracting 0 times 0. Okay, now in both cases, that's just 0, right? 3 square roots of 3 times 0 is 0, and then 0 times 0 is 0. So we're going to have 0 minus 0 multiplied by vector I, and then we're subtracting the next term, where we're going to be multiplying by vector j, and then we're adding the last term, where we're multiplying by vector k. All right, now for this second term, we're going to be looking at vector j in this first row, and we're going to cross out that row and the column that vector j is in, and then work with the remaining 4 values to calculate a 2x2 determinant. We'll multiply 3 by 0, and then subtract 0 times 5. Now once again, both of those are going to be 0, right? 3 times 0 is 0, and 0 times 5 is 0. So we're going to have 0 minus 0 times j. And then finally, let's work on our last term where we're multiplying by vector k. In this case, we're going to look at k in that first row, and we're going to cross out that row and the column that vector k is located in and calculate a 2x2 determinant with the leftover values. In this case, we'll have 3 times 0 minus 3 square roots of 3 times 5, and we finally have something that's not going to be 0, right? 3 times 0 is 0, but then 3 square roots of 3 times 5 is not 0. So we're going to have 0 minus 3 square roots of 3 times 5. And that will be equal to 0 minus 15 square roots of 3. Okay, 3 times 5 is 15, so multiplying these two values together gives you 15 square roots of 3. And so now if we simplify, both of these two terms are 0. Our x and y components of this vector will be 0. And so we're just going to be left with 0 minus 15 square roots of 3 times k, which will just give us negative 15 square roots of 3 times vector k. So that vector right here is the result of the cross product between vector v and vector u. Now what we have to do to find the area of our parallelogram is find the magnitude of that vector, right? The area of our parallelogram will be equal to the magnitude of vector v cross vector u, which will be equal to the magnitude of negative 15 square roots of 3 times k, this vector right here. And here's what that will be equal to. We're just taking the square root of the sum of the components of this vector squared, but two of the components are 0, right? The x and y components are 0, but then our z component is this value right here. So all we're going to be taking the square root of is negative 15 square roots of 3 squared. But then, of course, taking the square root of a value squared will just give you the absolute value of whatever that value is, right? If we square 15 square roots of 3, we will get a positive value, which we are then taking the square root of, which will also be positive. And that's just going to result in positive 15 square roots of 3. That will be the area of the parallelogram. Okay? And so now you can see that it doesn't matter which of these formulas you use, the area of the parallelogram will be the same. You get the same exact answer no matter which formula you use. But like I said earlier, you're most likely going to be working with this first formula where you take the cross product of two vectors that represent the adjacent sides of the parallelogram, and then you take the magnitude of that vector to find the area. Okay? And just like I said earlier, don't forget, this is a measurement of area, so the units would be squared. And of course, 15 square roots of 3 is approximately equal to 25.98 and some more decimals. And so that's it for this example, but let's take a look at one more example for this lesson video. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so here's our last example. We want to find the area of triangle ABC given vertices A, B, and C. Now A is the point 155, B is the point 695, and C is the point 572. All right, so this is a little bit different than our previous example. We're not given our vectors explicitly that will represent our given shape. In this case, it's a triangle, not a parallelogram, so we're going to be using slightly different formulas. But we can still find the area of this triangle using vectors and the cross product. We just have to first find the vectors using the vertices that we've been given. All right, and so let me show you what I mean by that. Our triangle is going to look something like this, where this vertex could be point A, this vertex could be point B, and this vertex could be point C. We want to find the area of this triangle using vectors, and so what we would have to do is find two vectors that would represent two sides of this triangle. And so you have to be careful about how you choose these vectors. Remember that you want to make sure that both of them start at the same point, at the same vertex. And so what you want to do in these problems where you're given the points of your shape, whether that be a triangle or a parallelogram, what you want to do is just pick one and then make two vectors from that point. And so in this case, I'm going to choose point A, and I'm going to find the vectors that look like this. Vector AC, right? This would be vector AC, and then I'll also find vector AB, all right? This vector right here. Notice that both of those vectors are starting at the same point. You don't have to pick the same vectors that I'm picking here, but just make sure that whatever you pick, they start at the same point. You could choose vector BC and BA, or CB and CA, doesn't matter, just make sure that you start at the same point. In this case, I'm just going to work with point A, so we're just going to be looking at vector AC and vector AB. Okay, and so once we find those two vectors, then all we have to do is take the cross product of those two vectors, find the magnitude of that cross product, and then multiply by 1/2. All right, that's going to be our method for finding the area of this triangle. This second formula doesn't really apply to this particular example because we don't have the angle between any of our adjacent sides, or the angle between our vectors. We could find it using the formula for the angle between two vectors, but that would be a lot of unnecessary work that we don't want to do in this case. Let's just find these two vectors and take the cross product, find that magnitude, and multiply by 1/2. All right, so this formula is always an option, but you're probably not going to use it that often. And so don't forget about it, but in this case, we're not going to use it. So I'm going to erase it here. We don't need it. We just need to use this formula right here. Okay, but now let's work on finding these two vectors. Let's start by finding vector AC. That's going to be equal to the vector where we subtract the coordinates of the initial point from the terminal point. So we're going to take the coordinates of C and subtract the coordinates of A. So for the x component, we'll have 5 minus 1, that's 4. So we have 4 comma 7 minus 5, which is 2. So we have 2, and then we'll have 2 minus 5, which is negative 3. So we'll have negative 3. And then let's find vector AB. That's going to be equal to the coordinates of vector A subtracted from the coordinates of vector B. So we'll have 6 minus 1 for the x component, and that's equal to 5. Then we'll have 9 minus 5 for the y component, and that's equal to 4. And then we'll have 5 minus 5 for the z component, and that will be 0. Okay, so we have our two vectors that represent the adjacent sides of this triangle. They both start at the same point, and so we can take the cross product of these two vectors and then find the magnitude of that vector and multiply by 1/2 to find the area of the triangle. So now let's work on that cross product. Let's figure out what vector AB cross vector AC would be equal to. And by the way, it doesn't matter the order in which you do this cross product. You could have AC cross AB, and even though you would get a different vector, it would just be a vector that is the negative version of this vector. When you take the magnitude of that vector, you will get the same result. Okay, so typically the order of your cross product does matter, but in these problems where we're calculating area and you're going to be taking the magnitude of that cross product, you don't have to worry so much about which vector comes first. Okay, so that's just something to keep in mind. Don't get too worked up over that. When you're calculating area, you don't have to worry about the order of your cross product. All right, but anyway, let's calculate this cross product. We're going to have vector I, vector j, and vector k in the first row. Then we'll have the components of vector AB in the second row, and the components of vector AC in the third row. So we'll have 5, 4, 0, and then 4, 2, negative 3. Those are just the components of each of those vectors. Okay, and so let's calculate this cross product. We're going to start by looking at vector I, cross out the row and the column that it's located in, and then use the remaining 4 values to calculate a 2x2 determinant. So we'll have 4 times negative 3, which is negative 12, minus 0 times 2, which is 0. So we'll have negative 12 minus 0, and that will be multiplied by vector I. Then we're subtracting a value multiplied by vector j, and then we'll be adding a value multiplied by vector k. All right, and so let's look at vector j now. We're going to cross out the row and the column that it's located in and work with the remaining 4 values. Let's take a 2x2 determinant. So we'll have 5 times negative 3, which is negative 15, minus 0 times 4, which is 0. So we have negative 15 minus 0. And then finally, let's look at k. We'll cross out the row and the column that vector k is in, and then work with these 4 values to calculate a 2x2 determinant. We'll have 5 times 2, which is 10, minus 4 times 4, which is 16. So we'll have 10 minus 16. Okay, now if we simplify, and I'm going to write this up here, this will be equal to negative 12i plus 15j and then minus 6k, okay? Negative 12 minus 0 is just negative 12. So we have negative 12 times I. Then we have negative 15 minus 0, which is negative 15, but then this negative sign is going to make that positive. So we'll have plus 15j right here. And then we have plus 10 minus 16 times k. 10 minus 16 is negative 6, so we have negative 6k. All right, so that's the cross product of vector AB and vector AC, the two vectors that represent adjacent sides of our triangle. And now what we want to do is take the magnitude of that cross product and then multiply it by 1/2, and we'll have the area of this triangle. So let's do that. The magnitude of vector AB cross vector AC will be equal to the square root of the sum of these components squared. And this is why the order of this cross product doesn't matter when you're calculating area, because if you swap this order here, you would get a vector like this, but these terms would be negated. So you'd have positive 12 and then negative 15 and then positive 6. And when you take the magnitude of that vector, each of those components just gets squared anyway, so it doesn't matter what their sign is. When you square them, they all become positive, and then you add them together and take the square root. So that's why the order doesn't matter when you're calculating area using the cross product. Other than that, the order of the cross product will matter because those components would be negated. Okay, so usually you want to pay attention to that, but for area, doesn't really matter. And so let's calculate this here. We'll have negative 12 squared and then 15 squared and negative 6 squared. And we're going to add all of that together. So we'll have negative 12 squared plus 15 squared plus negative 6 squared. If we simplify, that will be equal to the square root of 144 plus 225 plus 36, right? Negative 12 squared is 144, 15 squared is 225, and negative 6 squared is 36. If we add these three values together, 144, 225, and 36, you'll get 405. And so I'm just going to erase this and write the square root of 405. And 405 has a factor that is a perfect square, in particular 81. This would be equal to the square root of 81 times 5, and you can check me on that. 81 times 5 is 405, and 81 is a perfect square. It's equal to 9 squared, so we can simplify this again and say that it's equal to 9 square roots of 5. All right, so that is the magnitude of this cross product, but it's not our final answer. This would be the area of a parallelogram where these two vectors are adjacent sides. All right, so you can imagine that if we had a parallelogram here, that would be the area of that parallelogram, but that's not what we have here. We have a triangle, which will be half of that area. So the area of our triangle will be equal to 1/2 times the magnitude of the cross product between those two vectors, which is 9 square roots of 5. So we have 1/2 times 9 square roots of 5, which doesn't really simplify nicely. We're just going to have 9 square roots of 5 divided by 2, which would be the exact answer, but if you like approximate answers better, it's approximately equal to 10.06, all right? And there are some more decimals after that. Okay, and no matter which answer you use here, just remember that the units would be squared units since they represent a measurement of area. Okay, and so there you have it. We now calculated the area of a triangle given its three vertices by first finding some vectors that both started from the same point, taking their cross product, finding the magnitude of that cross product, and then multiplying it by 1/2. And so that's it for this lesson. But if you do want to see some more examples, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.